Hey everyone. So today I was able to get one of my FAANG engineer friends on a call so he could run a mock interview on me. So during college, me and him did a lot of studying for interviews. We would run a lot of mock interviews on each other. And yeah, that was back before we got into the Bay Area pretty much or Silicon Valley. So we're pretty much going to show the process of how we would conduct mock interviews on each other. So he's going to conduct a mock interview on me, and then yeah, um, that's pretty much it. Do you have anything to say?
No, yeah, like you're saying, we'll just show like sort of what we did to prepare for interviews and sort of go through the process and yeah, show what we were how we were practicing leak code. So it's more like a realistic environment rather than something that you just do on your own for practice.
Yeah. And one thing about me and this guy is I've done about like 500 questions and he's done 800. So every single time that we would have to do a mock interview, it probably takes more time finding a question than actually solving the question. It's pretty funny. But today, like right before this, we found some questions that I didn't do. So we pretty much have them pulled up. And yeah, should we start with the first one? Because usually some companies are asked about two mediums in the span of one interview. Or what about, what's your experience? Is it usually two questions or one question?
Yeah, so usually it'll be like an easy medium and then a medium or a medium hard question. So like two questions, or it could be like a medium question with some follow-up that makes it more challenging or with some constraints. So yeah, typically you'll see like one with a follow-up or two questions in an interview.
Cool. And then how much time do you usually give candidates?
Depends. Usually like the process is like around 45 minutes for the interview, and then you'll have like some intro and you'll go through like the interview process at the start for like a couple minutes. Then you'll save like 35 minutes approximately for like the questions, and then you'll have like another 5 minutes for some follow-up or answer any questions that the candidate might have as well. So around 45 minutes with maybe around 35 minutes for the actual questions.
Nice. Cool. Yeah, that's similar to what I've experienced. So I guess let's just hop straight into the question and then walk me through the way that you would run it on a candidate.
Okay, sounds good. All right, let's start with 3301, which is maximize the total height of unique towers. So let's go through this problem, which you're given an array maximum height, where maximum height at a specific index denotes the maximum height the ith tower can be assigned. And your task is to assign a height to each tower so that the height of the ith tower is a positive integer and does not exceed the maximum height I, and no two towers have the same height. And then return the maximum possible total sum of the tower heights. And if it's not possible to assign heights for whatever reason, return -1.
I see. Okay, cool. Thanks for walking me through that. I'll I'll do a quick read and try to understand the problem and then probably work through or look through the couple of examples and just make sure that I understand what's going on there.
Sounds good.
So I'm just gonna take some notes right here. So pretty much, so we're given an array of maximum heights where the maximum height of I denotes the maximum height that tower can be assigned. Your task is to assign a height to each tower. So we need to assign a height to each tower so that the height of I tower is a positive integer and does not exceed that height. And then no two towers have the same height. Okay. So what we need to do, and then afterwards we need to return the maximum possible total sum of tower heights. If it's not possible, assign the heights, return one. So let's see. So when I'm just reading through it, you're given the heights of a maximum height. You're tasked to assign a height to each tower. So we're gonna be assigning heights to the different towers. So if we think about it, we started off with kind of a flat. You can see my screen, right?
Yep.
And there'll be sometimes a whiteboard, depending. I think on all the platforms now there's a whiteboard.
Yeah,
But
exactly. So you could draw
we
or
s-
like write
we
out your
start up
solution.
we start up with this, right? And then let's just say we have 2, 4, 3, 1. These are the caps, right? This one has a cap of 2. This one has a cap of 2. This one, the second one has a cap of 3, and then 4, and then 3. So one thing we could do is we're trying to maximize the total sum of tower heights. When can it not be possible? Okay, let's just look at this example first. So if we want to maximize this one, the output is 10, and if we assign them in a specific way, medium right here, so we can assign them as 1, 2, 3, 4. So what I'm thinking is, since we're trying to maximize like the total sum of heights, we probably want to build the highest tower first, because the other constraint is no two towers have the same height. So what we're gonna do is like find the place where we can build the tallest tower and kind of build one there. But then no tower can be that height anymore. But this is the maximum height that can be assigned. Okay, so that will give us 4. And then for any of these, we'll probably want to build a tower on the next biggest height. So that'll be this one. But now you can't do 3. So this one would actually be reduced to, like, the maximum height here would actually be reduced to 2. And then what we'd want to do is next build, or this was 3, is next build one at the next biggest height, which is 2. And then I guess the next one here is kind of 1. So the next step is to build one at 1, and that kind of gives us a result. So I'm thinking we use some sort of heap in order to figure out the largest tower to build. Or maybe we don't need a heap. Let me think. But basically my strategy is, let's walk through a second example first, and I'll just quickly say what I'm thinking is we try to look for buildings that are the tallest, and then we build that tower, and for sure we'll want to build it to the max, right? And then once we build that tower, we're just gonna have, if other elements are the same height, we're gonna have to pretty much reduce their possible height, because it's going to be 1 less than mine, essentially,
Right.
because it can't be the same as mine. And then we kind of want to just build the biggest towers one by one until we're done setting up all the towers. And then I'm trying to figure out why we have -1. Okay, I see. So this one, it's impossible to assign positive heights to each index, so no two towers have the same height. Because we're only allowed, we need to assign, yeah, we need to assign heights for sure. That's over 1. So this one we have 2, and then this one has 1, and then the most we can do here is 1. So we're gonna have 2 towers the same height, we return false. This one we just take 15 and 10. So yeah, what do you think about my what I'm thinking about there? Does it make sense, my thought process of picking the biggest one first, building that tower, and kind of reducing the possibility of the any collisions by 1?
Yeah, I think that makes sense. So how would you go about implementing that?
Let me think. So let me reverse this a bit. So what I'm thinking is we probably need some sort of heap in order to maintain the largest elements, and then pick from those largest elements. Once we have or we might not even need a heap. Let me think. what if we could just sort them? The like the most brute force way would be, let me think. Yeah, sometimes I'm trying to think of various approaches that I could do it, because the thing that I'm trying to figure out is what is the biggest what is the biggest basically for each element. I'm trying to figure out what is the biggest tower. We might not need a heap for that. We maybe we could just sort that or store, like I'm thinking of multiple options, multiple data structures to use. One is like a heap, one is just a list, and another is like a simple hash map. And then what we would do, yeah, um, maybe I'll just implement it using a heap. But the thing is, if we use a heap, when we update the frequencies of the other ones, actually, yeah, we could probably use a heap. Let's say we push the heap, right? We pop from
Yeah.
the heap, and then when we pop another element from the heap, we see if the top of the heap is the same element, and then we keep popping those up and then pop them in with a value of -1, essentially,
Um,
to kind of reduce their height.
so how would you it's not guaranteed that the next element is going to be at the top of the heap though, right?
Which next element?
So you're saying that like you're gonna um or are you saying like you're popping from the heap afterwards?
So yeah, we do four. Let's say this is what our heap looks like: 4, 3, 3. So to figure out the best one, right? We're gonna pop four out. Once that's processed, we're gonna have a heap that kind of looks like this, right? Then we're gonna pop three and then build that one. It's gonna
So you're
rearrange
saying
the heap, or we're gonna have three here, and we're gonna see that there's another. The next greatest element is also a three. So we should probably pop that out and then pop it back in with one less value, essentially.
why do we need to so and then you're gonna add it back to the heap and then afterwards you're
Basically,
going
it's gonna be like
to
this. Basically, I'm gonna pop this out the heap, so we're left with two. But since I'm gonna use three, I reduce one from it, and then we get a, like our next heap is gonna look like this.
so could you explain how afterwards you so let's say in that case you add two back, right? So how do you know the two that you're popping um is one that was reduced already or one that was in the heap originally?
One that was reduced already. Sorry, I didn't understand that question.
Yeah, so when you're saying you're gonna pop it and add it back in.
Yeah.
Um so how do you know like let's say you added two, like you're like, okay, so the three already exists, so you need to add two to the heap, right? Because you need to reduce it by one.
Hmm.
And let's say you pop from the heap again. How do you know, or like what are you gonna, how do you know like whether that that two is one that was already subtracted by one, or if it was like originally two?
Like I think it wouldn't matter, because we're just readjusting the height, the maximal possible height. So pretend it used to be three, and then we've already seen a three. Oh, so pretend it was three, and we've already seen a three. Then it won't, like it could never be three anyways. So two is fine there. Sorry, let me find where was that? Okay, let's just like work through.
Yeah, sure.
Basically, what I think is it doesn't matter, because pretend this used to be a three, right, and it got reduced because we decided to process this three. it can't be 3 because it'll collide with another tower we set up. So at most it could be 2. So all of the elements in the heap are towers that we never built yet, and their value is the maximum height that we can make for that specific piece of land that we never built on yet. So pretend for sure we'll build on 4 and we'll maximize it.
Yeah.
Then we'll build 3 and then maximize it. But all the other 3s, we want to reduce them to 2. So essentially, it just helps us quickly find the ones that are 3 will move to the top of the heap, because if 3 is the last one we popped out, pretty much all the 3s are gonna be right behind it on the heap as we pop it out, or as we peak, because they're the same value. If that makes sense. So we could just pop it out, reduce the count, and then pop it back into the heap, and it'll be 1 lower. So that'll reduce this to 2, and then we'll be left with 2 and 2. We'll pop 1 out of the heap, which is 2. Process it, and then pop this 2 out, and then move it back in as a 1, and then that one we know can only be a 1.
Okay, so let's say let's run through like the time complexity of that if you're adding it back into the array, right? So if it's if let's say there's 100 values, and let's say let's say the length is 100, right? And then every single value is 100. What would the time complexity there be?
Yeah, you're right. It would be super slow because you have
Because
to
you need to
pop
like
everything.
decrement it by 1 and then add it back to the heap, right?
Yeah, yeah. So
So
I'm
it'd be like
thinking
n squared
is
log n.
yeah. So what I'm thinking maybe is what we do is we probably just need to keep track of some sort of frequency counts. And if we have, say we have 4, we have about 4, or for 4 we have 1 of those. For 3 we have 2 of those. For 2 we have 1 of those. We build at 4, that's fine. And then when we build 3, what we'll do is we'll build a 3, but then we'll add the remainder to 2. Pretend 2 doesn't exist there. We'll turn 2 to the 1. But then we'll just look for the remainder and add it there. And then we'll process like the next value, which is 2. Does that make sense?
Yeah, I think that makes sense. So basically, you're going to store this in some hash map or
Yeah.
like a
We'll store
dictionary.
Yeah, we'll store our hash map of the frequencies, and then maybe we could still maintain some sort of heap so we know like the next value. But basically, if we pop something out of the heap, it might not be there anymore. It might not. It might be a value that's already been decreased off. So what we can do is skip it, essentially. So we could use a hash map with the heap in order to solve this problem. That's what I'm thinking. Or depending on what the values are, we could just keep maintaining. Yeah, I'm thinking of a hash. I think if we use a hash map with a heap, we'd be able to solve it fast. And
What
pretty
if,
much. Oh, go ahead.
yeah, so could you think of something simpler maybe? Like, let's say if you put this in order, like if you sort that, right?
Mm-hmm.
If you sort maximum height, you'd be able to know how many elements are the same value by looking at the basically the neighbors, right?
Yeah, I see.
So do you think there's some way
Oh yeah,
to
actually,
solve it that way?
yeah, because I think also one part of this too is you don't really care about the indices at all. So what you can do is, since you don't care about the indices, this would be like a n log n operation as well, because you have to sort it. But what you can do is pretty much sort it and then convert the array into a non-decreasing order. So if we have 4 and 3, we have 4, 3, 3, 2. What we can do is 4 and 3. We reduce this one 2, and then like we do kind of one pointer around here, and we keep trying to reduce the one to the right. Yeah, I think the time complexity might be similar because it's we have to sort it, but we'd be able to that would work as well, and I think it's a bit simpler. So for example, for this case, 2 1 1, since we don't care about the indices, we kind of sort it. It's already sorted, but what we'll do is 2, we'll reduce this to 1, and then if we ever see anything that gets to 0, we return -1. Otherwise, after we'll take a max.
Oh,
What
we
is
want the sum, not the max.
or sorry, yeah, we'll take the sum of what's left there, as long as all of them we don't see a 0. How does that sound?
Right. I think that that solution makes sense.
Okay, let me implement that. So we're gonna take our maximum height. And what do you think about the time? Do you think it's so the time complexity I'm saying is n log n? It would be n log
So
n.
let's take a look back at your dictionary solution. That would be n log n as well, right? Because if every single value is unique, then you still need to store all the keys and then
Yeah.
sort those to know the
I'll
minimum or the maximum.
yeah, I'd store all the keys, and then so pop 4, and then I'll say 3 and 2. I'll reduce, or when I get to 3, right? Yeah, then yeah, it'll just be a lot more complicated, but yeah, I think that this approach makes sense. Let me go with the one with sorting.
Okay, sounds good.
So I sort the list, so I get 4, 3, 3, 2, 1. And what I'm gonna do is for every single element, afterwards, what I'm gonna do is return the sum of all of the building heights. So what I'm gonna do is I'll be able to sort this list here, and then I'm just gonna work from the left to the right. So I'm gonna say for index in range, and let's start with the first one, and then we'll run it all the way until length of maximum height -1. So what we're gonna do is we'll have I mean, we could probably store the result, but I'll just store the what we're gonna do is for every index, if index, so pretend we have a bunch of 4s here. So if the index beside me is the same, I'll reduce it. And so I can't just look for equals. I need to look if it's greater than or equal, and then I'll reduce it to 1 less than me. So I'll take maximum height at the specific index. If this value is less than or equal to maximum height of my neighbor, what I'm going to do is I'm going to take my neighbor and I'm going to set, so 4 here, right? I want to set the maximum height of my neighbor equals my height -1. That will reduce this to 3. We move on to this one, and then for this index, it's less than and equal to me, so I'll set this to 2. And then finally, I'll set this to 1. And then what we're gonna do is if for any value, basically what we're gonna do is for lm, one last pass. If the lm is less than equal to 0, return -1. So if any element kind of gets below 0, I mean, I could set that here. Let me see. Wait. What I could do. If this is less than equal to 0, return -1. Something like that. How's that look? Should we walk through it or just run it? Wait for index.
Um,
4, 3, 3.
yeah, you could walk through one of the examples.
Okay. So let's say this got sorted. This got sorted. So we got 4, 3, 3, 2. So what we have 4, 3, 3, 2. So we're looking at the index. If the element at this index is less than and equal to that one, that's not the case, so we move forward. If the index here is less than and equal to, it's equal to, so what we'll say is the next index plus 1 equals
So could you, for line 5, if the current index is less than or equal to...
the one
Oh,
beside it.
I see what you mean. Yeah, yeah.
So I'll do 2 here. So I'll say this one is equal to myself minus 1. And then when we go here, well, this one is less than, it's the same. It's equal to, so we get here. So this returns 1. I think that'll work. And then we just return the sum if none of them are equal to 0. And then
Yeah.
let's walk.
One thing is, what does sorted do it in an ascending order or descending order in Python by
Yeah, you're
default?
right. You're right. It's ascending, so we just need to reverse. Then cool. Let's hop on to the next question.
And then could you just walk through the time complexity and where, yeah, what that would be like for each operation there?
So for each operation, so sorting is of n log n and log n, and then pretty much we do the one pass here, which is O of n, and then lastly here, it's like pretty much O of n is here as well. So this operation is O of n when we're actually updating the heights. And then this operation is O of n as well when we're actually taking the sum of the heights. So in total, this is the worst time complexity. It's like n log n plus O of n plus O of n. So we get a time complexity of n log n. And then we don't use up any extra space because we're just modifying the same height. But doing this sort usually takes space because it's like usually a merge sort. So I'd say the space complexity would be log n for merge sorting. Or actually it creates a copy. So time complexity is O of n. And we could probably do this all in one go and not take the sum, but is this okay?
Yeah, that makes sense. And yeah, thanks for noting that. You could, yeah, like for the sum you could add it in, but for this purpose it's fine because it doesn't change the time complexity.
Sounds good.
Yeah, let's move on to the next problem.
Yeah, that was probably a bit more. I like your solution. That didn't really come through my head. When, like, for an interview, would you fail someone if you had to give them that much of a hint? Be like honest.
I think it would depend on, like, in a interview, I think I would give the candidate more time, and then I would also probably let them implement that solution, like the solution that you had, and then it just depend. It would be case by case. So it's like if you could correctly implement, if the solution that you're proposing with like the hash map worked correctly, and then also like you could identify the time complexity and space complexity correctly, it would be like borderline. But like in a real interview, I'd probably depends on like what the time constraints were, change like how I was giving the hints.
Okay, I see. Yeah. I didn't think of the sorting. Still, I need to remember those. Because, yeah, we need to be able to track collisions. So usually when it comes to tracking collisions, when you sort them and you get the ones that would collide adjacent to each other in the array. So that's a good. So let's move on to this one. Would you want
Sounds
to
good.
walk me through the question?
Yeah, sure. So let's go. Let's just read this problem out. So you're given an n by n binary matrix grid and an integer health. You start at the upper left corner, which is the 0, 0 coordinate, and you want to get to the lower right corner, which is m minus 1, n minus 1. And you could move in, what is this, four directions here. So up, down, left, or right from one cell to another, only as long as your health remains positive. And then a cell with a value 1 are considered unsafe and reduce your health by 1. And then we want to return true if you could reach the final cell with the health value of 1 or more, and false otherwise.
I see. Okay. Let me think. So our goal. Let me quickly read through it as well. So you're given an n by n matrix grid and an integer health. We want to start at the top right corner, and we want to get to the lower right corner, and we can move up, down, left, right, as long as our health remains positive. Cells ij are considered safe and reduce your health by 1, or considered unsafe. So when we hit this one, we reduce by 1. So return true if you can reach the final cell with a health value of 1 or more, and false otherwise. So kind of this one you have to kind of walk through. You kind of had to walk through ones in order to get to the bottom right cell. And then this one, where do you start? Okay, you start at 0, 0.
At the top left, yeah.
So what I'm thinking for this approach, super, maybe it's overly complicated, but I think we could run sort of like a Dijkstra's algorithm where pretty much what we want to do is we want to pop our neighbor, or we want to add our, pretend here we start with health 3, right? Or wait, let me think about it for a second. Let's walk through the test cases. That it might make it easier.
Okay.
Um, so this returns through the final cell can be reached safely by walking through here. This grid return false because you kind of had to walk through one of these. You kind of have to walk through one of these in order to get. You have to walk through one of these, and this is gonna get you 1.
So basically there's no path with like less than 2, what is that? Walking through less than 2 cells, basically, because you
Yeah,
have a health of 3 and we want to end it with at least a health of 1.
yeah. Okay, I see.
So for example, if that was 5, then we could return true there, because like the minimum's 4 health points to reach the final cell.
Yeah. So what I'm thinking is, what the reason why I'm thinking of a Dijkstra's sort of algorithm is for each cell, we kind of want to navigate from that cell using the most life possible. Or we want to, yeah, we want to know for each cell what's the highest health that I could reach that cell with, for example. So pretend for if we were looking at this one, pretend we had 0, 0. For this one, so yeah, basically I'm thinking of using a Dijkstra's algorithm. So and then we'll keep popping out the one, we'll keep a max heap, and we'll keep popping out of the heap the one with the maximum health. So we'll be visiting nodes based on maximum health. So it's a bit of a greedy solution, but we know that every time we visit a node or we're looking at a node, that is like we are able to get that node using the most optimal highest path, essentially, like the path that keeps our health the highest. And if we just pretty much do that for the whole operation. When we get to the bottom right, it will eventually give give us give us this node and the highest health that we've able to achieve to reach that node.
Okay, yeah, I think that sounds pretty reasonable.
Do you think there might be? I'm not sure if there might be a faster one. Maybe something of counting walls and stuff like that. Maybe there's a way that we can just count the number of walls that were hit. So we do like my breadth first search from here. So if we go, yeah, there might be approach where we count up the walls that are hit, and for each cell we kind of try to minimize it. But I think for me the Dijkstra's one is a bit more intuitive. What do you think? Do you think I should optimize on that approach?
We could implement the Dijkstra's approach.
Okay, sounds good. So what I'm gonna do is to run a Dijkstra's algorithm, we need to use a heap. And we're gonna start off at 0, 0. If we land on a 1, that automatically reduces 1, I think. So if we start on a 1, it automatically reduces the health, right?
Yeah, it would.
Okay, so what we're gonna do is we're gonna pretty much run a Dijkstra's algorithm, which we init priority queue, and then pretty much run through that priority queue until we hit this bottom right corner. So the bottom right corner or the elements of the bottom right corner are gonna be, and we can move up, down, left, or right, as long as your health remains positive. Return 1 if you can reach the final cell. So Python implement. Oh, sorry, I accidentally submit. Python automatically or uses a max heap, so we're going to have to use a. Pretty much it uses a max heap, so we're gonna, or it's Python defaults to a min heap, so we're gonna have to convert it to a max heap here. But what we're gonna do is we're gonna initialize the priority queue. So priority queue equals that. And then we're gonna first put in the 0th and 0. We're gonna put in the 0th and 0th column. So if it's a 1, we're gonna want to reduce the health. But what we're gonna store in our priority queue is something like this. We're gonna store a tuple of the row, the column, and the health that we were able to get to that column. And we're gonna time this by -1 since it's a max heap to get the max heap. Does that make sense?
Yeah.
Okay, so if and it's a binary thing, so we only have zeros and ones. So if the grid row at 0, or what's the possible dimensions? Is it 0 and 0? Can we have empty? Looks like we can't have empty, so we're good here. So we'll start with with the very top left element, which is 0, 0. If it's equal to 1, then for the priority queue, we'll append 0, 0, health -1. And we're gonna have to multiply that because we're trying to do a max heap. Times -1. So we're reducing 1 there. Or what we can do is if it's equal to 1, we just do health. Minus equals 1, and then we just do this. So we take our health and we multiply that by -1 to turn into a max heap, and then now we're gonna run our algorithm. We're gonna have to maintain some sort of scene array. So we'll do that in a second, but we'll do scene equals set, where we store tuples of the row and columns we visited. So pretty much while the length of the priority queue while the length of priority queue is greater than 0, what we're going to do is we're going to take the candidate, or we're going to take the row in the column and the health here. Candidate health. And we're going to do priority queue. We're going to do heap queue dot heap pop. We're going to pop from the priority queue the one with the highest health. And we're going to do count health times -1 to get it back into the health what we want. And then what we're going to, that's going to give us the one that's the place that we get the highest health. And then we're going to we're going to look through the neighbors, which are, we're also going to say that now we've seen this. And then what we're going to do is we're going to loop through our neighbors. So our neighbors are going to be pretty much, you said it's going to be top left, bottom right. So we're going to take our row and column, and I'm going to do it a little bit faster because time is running short.
Okay.
So we're going to do row, column, row, column. So what we're going to do is, to look above us, we do row -1. For column, we do +1. Or to look to the right, to look under us, +1 here. To look to the left, column -1. So we're saying for neighbor row in neighbor, or sorry, for neighbor row in neighbor column in our priority queue, or sorry, for neighbor in neighbors. If we're basically gonna do some bounds check. If the neighbor row is less than equal or less than 0, or the neighbor row is greater than or equal to the length of the grid, if the row is invalid, we just continue. We'll do the same thing for the column. Less than 0 or greater than. So we'll do the same thing for the column. And another one.
I think this is just a small typo there. 26. It's NEIGHB.
Oh, yeah, you're right.
The
column.
Column, yeah.
And then we'll do like this. Thanks for catching that. If this is already in scene, we continue. Otherwise, what we're going to do is, like, we also have to get this case too, where if let me see, if the row basically we have to be able to capture if we got to the bottom right. But let me just handle this case first, where we're looping through the neighbors, and for all of the neighbors, if it's valid and it's not in scene, what we're gonna do is we're gonna pop them into the max priority queue. PQ dot. What we're gonna do? Push. But it's gonna depend on what we're gonna do. We're gonna say it depends on if it's a 1 or not. We'll say is 1. If we'll basically look at the grid and access the row and column. If is 1, what we're going to do is we already multiplied the candidate health, and so if it's 1, it's gonna get to 0. So we need to reach value of 1. If it's 1 and the candidate health -1 is actually equal to 0, we don't want to pop it to the queue, right?
Right.
because we won't be able to get there, and probably will return false at some point if we could never get to the thing. But what we'll do is we'll heap push. What we'll do is we'll push, and actually we need to rearrange the elements of the heap because this should probably go first, the health. So what we're gonna do, and I'll fix that in a second. But what we're gonna do is we're gonna take our candidate health and we're gonna minus this by 1, and we're gonna take our neighbor row and our neighbor column. Right, we're gonna do heap queue, heap push, neighbor row, neighbor column, and then let me just quickly adjust how we're gonna do this. How does this look so far? Do you have any questions on my implementation?
No, this seems pretty clear so far.
Neighbor column. Then we're gonna have to multiply this by -1. Then we're gonna have to readjust some of this. Heap queue, candidate. Where is it?
Line number 8.
Line number 8. Oh yeah. Nice. So we're going to be given the health. This is gonna give us the top one, and then pretty much when we pop one out, we seen it. So if the row equals length of grid -1 and column equals length of grid 0 -1, return true. Or sorry, if we can get there, we return true. Something like that. Quite a bit of code. How's that look?
So for line 39, we're not always subtracting 1, right?
Yeah, you're right. If is 1, then we subtract. Else we just push it. Yeah, thanks for catching that.
Yep.
It's kind of slow. Might not be optimal. Should I run it on the submit and see if it
Yeah, you could try.
times out? There might be a... Oh yeah, it's gonna time out for sure. Oh, so it didn't time out, but it was just really slow. Start 1. Oh, we just need to capture this one test case of if the health equals 0, then we just return false right away. Could I try running it again?
Yep.
Hopefully it passes. If not, we'll... Oh, shoot. It's too slow. Let me think. Yeah, it's too slow. I need to figure out like a faster approach. So maybe I overcomplicated it again this time.
So I think in this case, I think it's correct. I think what's slowing it down is so I had something similar, but instead of scene using a set, I just initialized like a visited basically 2D array.
I see.
Yeah. So that could be what's slowing it down, but the solution looks correct to me.
I'll just use like the use in place the array. So instead of scene, I'll set it to 2 or something. I'll say the grid, the row and column equals to 2. And pretty much if the grid at the neighbor is equal to 2, continue. And I'll do the same thing. Yeah. Something like that.
You could try running it with just to double check. Yeah.
Might need to switch to C++. I feel like those ones don't fail, regardless if it's a scene or use the hash map or the array.
Yeah, I think it's a
Oh,
little
time
bit
limit exceeded.
more.
Yours was similar to this? What am I doing wrong? -1. Wait, I'm trying to figure out how I should manage the scene. Maybe if we add to the scene before, it will be faster. For example, if we add to the scene before, so we take the grid, row, and column, it will reduce the amount of things in the heap. So if we do grid row 0, and then we take our, we don't do this anymore, or sorry, 2 here. What do we do? Like when we pop it into the heap, we do it like this. I wonder if that'll fail. Wait, whoa. I'm not sure if the lot. Okay, that's gonna be a lot faster. Yeah, got accepted.
Oh, I think it was the I think you just weren't marking the first cell as visited. I think that was a bug. Yeah.
Or I changed up the order of when I popped it into the heap though.
But
Like
that wasn't there originally, right?
where?
I think it's the visited that you changed. Like if you just add that
Where was it? Where's my last solution?
grid row. Actually,
Wait, let me try. Let me reverse
because
it.
yeah,
See what you're saying.
yeah. Let's see. Looks like there was
For neighbor row. So where's my scene? Did I bring back my scene? Oh, wait, let me reverse it. So I was doing that before. Yeah. How did you do it? Were you doing it as soon as you threw them in there?
I was checking it. No, I was checking it in at the start of the while loop, basically right after you pop it.
Like after you add things into the heap, you marked it as visited, right? Or no?
No, when I pop it.
Oh, when you
So
popped it. Okay.
yeah, so it does
So
add
mine
a
was
couple
running.
more. Yeah.
I'm not sure if mine was. I'm not sure
But there
why
was
that
one that
was.
was accepted. So what would be like the time and space complexity for this problem?
Let me look at the one that I have. It would be pretty much if we say n is equal to, if n is equal to the number of elements in the array, it will be n log n essentially, or it will be n to the something like n times m multiplied by log m times n.
Yeah, that
I think
looks
that's
correct.
Dijkstra's
And then what
because we're just
about
popping
for
in and out of the
space
heap.
complexity?
The space
Yeah, that's
complexity.
right.
The space complexity is it would be the size of the priority queue. And how big can the priority queue get? It's pretty much my space complexity is probably m times n, worst case. But it might even be smaller than that because we're just processing one element at a time. one element at a time. But yeah, worst case, or it's yeah m times n of space.
Yeah, that sounds right to me.
Nice, cool. Looks like we're at the
Yeah, nice
top of the
work.
hour. Thanks. That one was. I can't do those array ones are messing me up. Any feedback?
I think the good stuff is like I like how you walk through the examples at the start of the problem. Like after first, it's like you'd clarify the question or read through the question, and then walk through examples.
Mm-hmm.
I think with like the first problem, we already talked about this, but just getting stuck on the heap was the tricky part. And then for the second problem, same feedback. So it's like, yeah, you walk through the test cases. It was clear that you're explaining the solution.
Mm-hmm.
Um, the couple things would be like there was some like small like off by one or like subtracting one small bugs. So it would have been nice to like basically walk through the examples after you have like the concrete implementation so that you might be able to catch those before they're pointed out.
Nice,
But that would be something that you might want to do in a real interview. But overall, it was good.
cool.
Nice work.
Sounds good. What's the optimal for this one? Oh, you have to use Dijkstra's or simple.
So there's Dijkstra's, and then there's like a M by N using some dynamic programming as well. So, but both
Oh,
both work.
yeah. The Dijkstra's one makes more sense to me. I wouldn't. I would. What's the elo on this one? 2 2. Damn, it's only 1600. I feel like all the people doing the contest kind of know Dijkstra's though. That's why
Yeah,
everyone
yeah.
knows
This
it.
is like a pretty typical, um, yeah, Dijkstra's question.
Cool. So what else? Yeah, that this one is a good question. How did you come up with this? Like, what was your thought process? Did you try similar approaches, or you automatically started thinking of the sort? And if you did think of the sort right away, how'd you iterate into that?
Yeah. So on my notes, what I have is greedy. So like first sort it in descending order, because the what we want to maximize is the next valid value, meaning that's going to be the max of the previous height minus one or height. So if like, and then um, and then if we get to the end, then we or sorry, if any of them reach one, then we return negative one, or else we um, return the sum of the values.
I see.
So I had something similar, except yeah, like with tracking the previous value, but you're just looking at the previous index, but something similar.
Cool.
But
All
yeah,
right.
just identifying like the staying ahead. So like knowing what the next value is based on the previous value.
Sounds good. I'm gonna. This gonna be part of the title, so you have to give me my rating. Is it no higher, higher, we, and you could be like soft higher, or how do they do the rating? Pretty much, just give me the rating, and don't hold back.
Um, I would say it's leaning towards higher. Like I was saying in the first question, I'd probably in a real interview um, approach it a little bit differently with like the hinting and also like what I'm expecting.
Yeah.
So like I think I was mentioning if you had implemented the solution you had correctly, and then you also correctly identified like the time and space complexity. Um, that's like the reason why I say yeah, like leaning towards a higher. But yeah, but then the second solution is pretty good. So that one would be a higher.
But do you have to keep it track both of the questions or no? Or do you,
Uh,
if they ask two questions,
usually,
or go ahead.
um, yeah, it's just like case by case, but like in this one, like since they're like pretty different, like um, that's why it's like but it'll be like for the overall interview would be
Okay,
uh lean higher.
let's see. Okay,
And then
nice.
also just based on the time too, because like we went a little bit over time, like we're almost at the hour.
Yeah,
But it would depend on like how long we had for the interview. If we had an hour for the interview, then that's fine. But if we only had 45 minutes, we probably might have not gotten to like the two complete solutions.
I see. Yeah. Damn, I need to iterate through my solutions faster. Kind of when I start thinking of one solution, it's hard for me to switch it up. Do you have any advice for that?
Yeah, I think one thing you could do is maybe write out like pseudocode, like some bullet points on like what the step by step would look like, and then that might help catch like the time complexity. Like for example, I think one of the solutions you'd proposed for this question 3301, it was like n squared log n, like because like you're basically pushing and popping from the heap multiple times, right? Like
Yeah.
the example where I gave, if it was like length of 100, and then you'd have to like basically pop it and then push it back like
Yeah.
that many times. So I think if you had that out in some pseudocode, like maybe you could have caught that it was like n squared log n, which might have hinted, like you might have recognized that that wasn't the optimal solution. So
Mm-hmm.
that's like one way. Other ways, similar to that, is like finding, uh, writing out test cases or edge cases that might point to, uh, might point to whether the implementation is correct or not. That's like another way. So like yeah, coming up with your like on leak code, it'll have like basically a couple test cases, but in an interview, you might want to come up with your own test cases too,
Mm-hmm.
just to make sure that your solution's going to be correct for those. So those are some ways that might
Ways.
help guide you back on the right track.
Cool. Sounds good. Uh, it's late at Sunday. I know you probably are gonna go golf, but thanks for your time.
Of
Hopefully,
course,
maybe we'll do one
happy
with
to.
you at some
Yeah,
point.
definitely,
All right.
definitely.
Okay. Sounds good. I'm gonna stop the video now.